Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Arnab Ghosh graduated with a Bachelor of Technology in Computer Science from the Indian Institute of Technology, Kanpur, in 2016. He is currently a PhD student working under the supervision of Professor Philip Torr at the University of Oxford, focusing on mathematical theory of computer vision and artificial intelligence. His primary interests lie in artificial intelligence with a focus on learning applications for computer vision and natural language processing. Before joining Oxford, Arnab worked as a research intern at the Toyota Technology Institute in Chicago and at Adobe Research in Bangalore. Viveka Kulharia graduated with a Bachelor's in Technology and Computer Science and Engineering from the Indian Institute of Technology, Kanpur, in 2016. During his undergraduate studies, Vivek held a research internship in the Machine Learning and Statistics Group at Xerox Research Center, India. He then worked as a research fellow for Microsoft Research India, working on cloud service modeling and improving recommendation systems for Office applications. Vivek is now a PhD student in the Torr Vision Group at the University of Oxford, working under the supervision of Professor Philip Torr as well. His research interests lie in the field of machine learning, deep learning, and Bayesian inference. Arnab and Vivek, I want to welcome both of you to Data Skeptic.
Thank you. Thank you for having us.
Thank you, Kyle.
Yeah, I was glad to get a chance to talk to you guys about your interesting paper, Multi-Agent Diverse Generative Adversarial Networks. And we'll get into some of the details on your specific contributions there, of course, but I thought maybe to begin with, it might be useful to talk a little bit about what general adversarial networks are. Could you guys give us the rundown?
We can think of GANs or generative adversarial networks as two networks playing a zero-sum game against each other. One of the networks is generator, which tries to generate real-looking images. The other network is a discriminator, which, when given an image, tells whether the image is real or fake, that is, generated by the generator. Both the networks always try to win against each other. The generator tries to fool the discriminator into telling that the generated image is real, while the discriminator always tries to guess correctly whether the image it receives is real or fake. For training this combination of networks, the discriminator receives a feedback about whether the image it was given was fake or real. Based on this feedback, the discriminator improves itself. The discriminator also gives feedback to the generator in the form of gradients so that the generator can improve itself and produce more real-looking images the next time.
When these two networks have converged, the generator becomes very good and produces very realistic looking images. And the discriminator at the perfect stage of convergence, the discriminator can't tell whether an image is actually generated by the generator or actually a real image. So in this manner, the generator can understand the image manifold very well.
Within my lifetime, we've gone from having almost no good technology for image recognition to having very powerful technology. So I think sometimes people take for granted that image recognition and image discriminators are coming around and being very useful. But I find myself continuously impressed with these generators. That seems like their problem is harder.
Yeah.
Can you talk a little bit about how you're able to go from presumably at the start of an iteration, maybe just white noise, and apply and leverage the gradients that are given to the generator to start making these often very realistic looking images?
So if we think about it, the major benefits of machine learning and especially deep learning have come from supervised learning, in which you're given an image, you know which class it is from. The classical VGGNet and ResNets have performed extraordinarily well on the ImageNet dataset. But the label data is actually very costly. You have to pay someone heavy price to actually label each data point, and that becomes very costly. So the real promise of machine learning is to have an unsupervised learning method. In this manner, in a game between the generator and the discriminator, there is no supervision required. You just give an image to the discriminator and it tells whether it's real or fake, and without any sort of labels provided, the generator is able to produce images. But coming back to your question of how these two players get better over time, one thing one has to keep in mind is that the discriminator is not pre-trained. These two networks start from scratch. these two are like two children. Like one is a thief child and another is a police child, right?
Yeah.
These both know nothing about images at all. Now, this generator, this small thief generator who knows nothing, starts generating images. And the discriminator gets these images from the thief and it said that, hey, look, these are false. These are absolutely junk images. And also, it's given real images, which it knows nothing about because it doesn't know what's real and what's white noise when it's starting, but just knows that hey, look, these are real images and these. But the point is that the discriminator is not trained more than the generator. They both take one steps of gradient, so both go hand in hand. Both bootstrap each other. Both help each other to get better. So the discriminator helps the generator to get better at generating images, and also the discriminator in the initial stages, the task of the discriminator is very easy. It knows that random junk is produced by the generator and very nice images are produced from the data real data manifold. As it goes on increasing, the task of both become difficult. The generator starts improving and generating more and more real looking images, and the discriminator has to learn finer boundaries between what's a real looking image and what's the image manifold that is learned by the generator. These both go hand in hand and bootstrap each other and help each other to actually get better and better.
Do you consider this an unsupervised learning technique then?
Absolutely. There is no supervision. You just give lots of images and it learns to generate images of that sort in an unsupervised manner. You don't need any label. You don't need to tell whether it's a dog and label a category as a dog. You just show images of the dog. It starts generating images similar to dogs. Because of this unsupervised learning, the discriminator knows a lot about how the real images look and also how the generated images look. The features of the discriminator can be later used for a downstream task. You train this set of generator and discriminator in an unsupervised manner on a set of images, and then after that, you just pass. When you have the labels, when you have some labels of like just 10 images with labels, you can leverage the knowledge it has learned on all the different unsupervised images. It can easily classify using just 10 image labels, whether it's a dog, whether it's a cat, or whether it's a tiger, or etc. So that's the basic promise of unsupervised learning coming to real fruition.
Yeah. That was going to be my next question. I wanted to ask you a little bit about the corpus size of images required to get up to levels of accuracy that are impressive. Could you talk about, how many images you guys trained your experiment on?
Right, because the discriminator is trained on millions of images without any labels, and it knows a lot about how these real images and also how these fake images look. Because it has been trained in such a large unsupervised corpus, very few data points from the label data is required. In our experiments, we had 10 categories, and for each of the 10 categories, we just used 1,000 images, right? 1,000 images for each of the 10 categories to actually get to levels of accuracy which normal CNNs would require millions of images, millions or hundreds of thousands of images.
Wow, that's a tremendous speed up then.
Yeah, yeah. It's not a speed up, but because first you have to train the discriminator in an unsupervised manner and then use the features of the discriminator for a downstream task. So it does not speed up, but the number of labels required, number of labeled data required is an exponential decrease.
Excellent point. Yeah, more of a bootstrap, not really a speed up.
Exactly.
The next question I wanted to get into was the mode collapse problem. Could you basically, I guess, define this problem? It was actually, I have to confess, I was introduced to the concept, or at least that phrasing of the concept, through your paper. So I'm eager to share with the audience, a pretty formal definition, if you don't mind giving one.
The formal definition is that there are lots of modes in the data distribution, modes being lots of high density data. For example, if you consider the ImageNet data, then all the images of dogs will be very close together, right? They're very similar, all the dog images, all the cat images. So each of these types of image, right? All dog images will be very close in the data space. All the cat images will be very close in the data space, and they represent the modes in the data distribution. Images of cars, images of buildings, all will be very different. Images of cats will be very different from images of dogs. And
Mm-hmm.
these two form the two modes of the data distribution. Modes statistically mean the places where density of data is very high. So the problem of mode collapse is that in the case of the game, so it's a game between the generator and the discriminator, what happens is that the generator only learns to model some types of modes. For example, if it is shown images of three kinds, dogs, cats, and buildings, it only learns some kinds of modes. For example, it will learn very good images of dogs and buildings and maybe not learn anything about cats. It will not generate any images of cats at all. So why does this happen? So the main problem is that in the case of the game, the generator only benefits if it can fool the discriminator. If it can fool the discriminator into thinking the image of a dog is the real one, it doesn't care if it generates a cat or not, right? In terms of the minimax game that these two are playing, it doesn't have any incentive. If it's already doing very well on certain types of modes, it doesn't have much incentive to try to distribute its data distribution to other kinds of modes. This is the main problem. That's why you see that the images of what it generates are really high quality and really very sharp. In the example I told, if it's given the task of generating dogs, cats, and buildings, it will generate dogs and buildings of really exceptional quality, but it will miss out on generating cats, absolutely, which is very important, right? I mean, you don't want to miss out on some part of the data distribution, which might be very necessary to train the discriminator to even get better, right? That is the problem of mode collapse or mode missing.
Got it. So I have a somewhat abstract question. Maybe there's no good answer for it, especially since widely people regard deep learning as sort of a black box. But I'm curious, as you're iterating through these adversarial competitions each round, trying to have the discriminator recognize and then give gradients back to the generator, are you able to assign any intuition to the generator as to what it's improving upon maybe early on versus later? In other words, does it start to learn textures and then light features, or is it just kind of learning in a very fluid fashion?
There have been several works on trying to analyze, like we can always examine what the generator has learned by generating millions of samples from that distribution, from that generator. So that is one way in which we can do that. But you're right, actually, what happens is that at the initial stages, the generator learns crude features. Actually, in terms of training the GAN, easier to know what exactly is it's learning at the different stages of training by just getting some samples out of the generator. That's very simple. You just generate lots of samples and you see what it's generating. In my experience, what happens is that in the initial stages, it learns to do crude kinds of faces, where it learns to see where the eyes are, where the lips are, where the nose is, and where, how, different types of hair color. And slowly and slowly, it gets better and better. As the training progresses, it starts to generate more sharper features, more finer details of the faces, more finer details of the eyes, more finer details of the eyelashes, and goes better and better.
Yeah, so texture is learned on the later stages.
Yeah.
Initially, it is form, so where the eyes are.
Let's take a break from our show today to discuss our sponsor, Periscope Data. I've told you on other episodes about how easy it is to go from SQL into interactive dashboards with Periscope Data. What I want to highlight this week is their cross-database joining capability. Unless you're a recently launched startup, you've probably got multiple databases in your company. I talk to a lot of data science teams that are struggling with tedious engineering work, trying to connect these disparate data sources. With Periscope Data, many of those concerns can be set to the side since they can handle cross-database joins for you. Now I know what you're thinking. How can that work for me? I connect to huge databases and there's no index shared across them. Even if Periscope Data allows the join, those queries are going to be full database table scans, right? That's what I thought too, but I was wrong. Periscope Data has a caching system they've built that sets all those concerns to the background. You specify the database server, name, and table, and regardless of where your system of record lives, Periscope Data will efficiently manage the cross-database join. If you've got multiple places you pull data from, and would like a better solution for merging it all together, head over to periscopedata.com/skeptics to start a free trial. Once again, that's periscopedata.com/skeptics. So getting back to mode collapse, as I understand it, one of the novel contributions of your paper is taking the multi-agent approach to try and get more diverse generators. What was the inspiration to do that, and how did you end up implementing it?
So the inspiration is that in terms of the American and the Western capitalistic society, the different companies, if you see, they focus on different types of problems, right? The different companies are very focused on different types of problems, and they compete among each other. And this competition, the healthy competition, actually improves all these different companies to actually get better at their individual tasks and also to really focus. If a single company tries to solve all the problems, it just fails, right?
Mhm.
We had seen previously that a particular GAN was able to do really good on generating faces. A particular generator was used to generate digits. A particular generator was used to generate street view house numbers. But a single generator to do all these different kinds of images together is very difficult. So we thought, let's divide and conquer. Let's divide these different modes to different generators so that these generators would only focus on particular modes and try to get better and better at only those kinds of modes. And therefore, the idea of multiple agents came. The two innovations we have in our paper, I'll explain one by one. Actually, the two are motivated by different kinds of ideas. The competing objective is framed such that I try to make my generations so that I get better scores for my generations from the discriminator than Vivek's, and Vivek does the same. We try to compete among each other to get better scores from the discriminator, better real looking scores. Basically, the discriminator can be thought of telling, hey, look, you give an image, how real it is. If it's close to 1, it's very real. If it's close to 0, it's very fake, right? I'm competing with Vivek to get better scores from my generations. And I also have a dissimilarity term so that my generations are very different from Vivek's. What I generate has to be very different from Vivek. We can't do the same thing and get better scores. We have to get different kinds of images. We have to, for example, if I concentrate on dogs, Vivek doesn't get much benefit from beating me at dogs. He gets more reward if he focuses on cats and generates better looking cats. That fools me, that fools the discriminator, and also is different from my dog looking images. So that is the first way in which we try to push the different generators towards different kinds of modes so that they can do different kinds of generations by trying to beat each other and also trying to generate images which are different from each other. The second approach to actually divide this task of distributing modes between the generators. So first I'll tell the motivation. Imagine a professor. He has his particular research area and he wants to have multiple projects to be done. So the way, and that is very similar to how the discriminator and the generator is. The discriminator is like the principal investigator who guides the generator into generating good images from the data manifold.
Mhm.
If there is a single student and he's tasked with doing all the different kinds of projects, he'll inevitably fail. So let's have multiple students, and the professor divides his projects into different students so that the different students can only focus on a particular kind of project, and in our case, particular kinds of modes. And also, his task is to identify if there is a discussion of a project, which student is doing this project. He has to divide the projects in such a manner so that he can easily identify, hey, look, this student is doing this project. And therefore, in this manner, the task of the different projects, or in our case, the different types of images, are divided among the different generators, and the generators become better at doing those kinds of stuff only and not at trying to do everything, but only fixating on those kinds of particular stuff.
I like your analogy of the principal investigator kind of shaping where different contributors are going to work. But that, in some sense, makes it sound like a supervised learning problem, that you have the discriminator pushing them each in new directions, where we've already covered this is more of an unsupervised learning problem. So could you talk maybe a bit about how the agents coordinate and make sure that they're not all learning the same modes?
By training the discriminator, we get the images from all the different generators, and then we tell, hey, look, this generator is producing this kind of image. The earlier task was just a two-way classification problem, whether it's real versus fake. In our setting, the generator identification setting, it's k plus 1 way problem, classification problem, where there are k generators and there is one real class and there are k fake classes. So the k generators generate images which are considered to be fakes from each of the k generators. Now, how it is trained is that the discriminator sees an image and tries to predict the correct class if it's a fake. If it's a fake, which of the n fakes generated this particular image, right? If it has to win in this task of correctly predicting which among the k generators produce this particular image, it has to learn to push these different generators towards different kinds of modes because the gradients of the generators comes from the discriminator. If it has to win in this task of predicting which among the k generators produce this particular fake, then it has to learn to push the different generators towards these different kinds of modes of the data distribution. There is no explicit label use. This game is formulated in such a manner that it becomes kind of a supervised problem, but a meta supervision,
Yeah,
not
yeah.
an explicit supervision.
Do you guys have any best practices on selecting the number of generating agents?
Our framework of multiple generators only help if a single generator can't do a particular problem. If a single generator can master a particular kind of problem, then you don't really need multiple generators. But in current research, whatever has happened up till now, there is no single generator that can produce different kinds of query on a very large corpus. So that's why in cases of ImageNet, we tried up to 5 generators and it worked pretty well. I mean, the more the better in that case because that's a pretty difficult problem to tackle. But the current limitation is the size of GPU. The GPU only has 12 GB of memory, so that is the current limitation. But in cases where a single generator can't do, having more and more generators will help. But in cases where a single generator can master a particular problem, you don't need multiple generators.
And can you talk a little bit about how you calculate the similarity between two of the objects?
We wanted to be unsupervised, and that's why we thought we would leverage the training of the discriminator to actually see how different the two images are. So what happens is that we pass the generated images from both the generators through the discriminator. We take a particular layer of activation of features from the discriminator that forms a vector, and we compare it using cosine similarity, how similar these two uh, vectors are. In the traditional cases, the discriminator knows a lot about how images look, and therefore, when you pass the images through the discriminator, it can tell higher level features of how these two images look, and they want to be compared using a cosine similarity. It will tell how similar these two vectors are.
I'm going to encourage everyone to go and take a look at your paper. I will put a link to in the show notes for everyone to find that pretty easily. There are a lot of example images that are very compelling. In particular, like you have some landscapes and some faces and a couple of handbag type products.
Mhm.
One thing that I noticed was, I think the state of the art for everything all human beings are working on is still not perfect with faces yet, but we're getting close.
Yeah.
Yet in the case of the backpacks images that your generators are making, I
Yeah.
have to confess, I think you could have fooled me. So
Yeah.
I'm curious if you're finding that there are upper limits simply because the images are almost indistinguishable from real.
Absolutely. I mean, when I was training these models, I was surprised at how good these kinds of bags were and how good it was almost designer quality.
Yeah.
This is a slightly different kind of task in which the sketch is given. It is not a completely unsupervised approach. It can be thought of as the supervised approach because you know the actual bag and sketch, and that's why it's much easier, I would suppose.
Hmm.
But this is actually slightly different from the totally unsupervised case. I'll briefly explain how this works. This is called the pix-to-pix architecture, which was not our work. We built on top of, we had a single agent version of pix-to-pix and we had the multiple agent version. So what happens is that you're given a sketch, the generator gets the sketch, and it tries to generate a real looking bag out of the sketch. Now the discriminator gets both the sketch and the bag and tells how good it is. It gives a score between 0 to 1 of how good this particular sketch. It's not exactly an unsupervised problem, but the technique is same. The discriminator really helps. As you can see, our bags are better than the original pix to pix because the discriminator is dividing the task among the different generators so that it focuses on particular types of textures and particular types of colors. And because it is focusing on a particular kind of texture and color, it's generating better than if a single generator had the task of generating everything.
And I wanted to ask a little bit about the computational costs here. Comparing it to, let's say you were just doing a single agent type approach. Naturally, the multi-agent is more computation, but does it scale up linearly, at n times as long for n number of agents, or are there efficiency gains you can share in the iterative learning?
If you think about it, if you want to generate some drawing, most of the earlier stages are very early stages of computation by the different generators are very similar. Okay? They'll try to understand what hair is, what nose is, what different kinds of basic features. And the last layers would help in fine tuning of these kinds of features. So that's why we gain computationally by sharing much of the parameters of the earlier layers and just keeping the last layers different. And therefore, when you want to scale up, it doesn't scale up linearly, very slowly, because just the last layer of the different layers is different, and rest all the layers are shared between the different generators.
What are some of the potential applications you guys see for your work?
There are lots. I mean, many of these problems can be considered as image-to-image translation. So we can have different kinds of, whenever there is an under-constrained problem, for example, you give a night image, there are multiple plausible day images based on whether it's sunny, whether it's cloudy, whether it's evening, whether it's morning. There are different plausible scenarios for corresponding day images. You can use them to create multiple plausible futures. You have a video of a particular number of frames. You want to see how it's going to happen in the future frames, what is going to happen in the future. So you can have multiple plausible futures, which can be potentially useful in training self-driving cars. And for example, in the future, when these kinds of sketch to real-looking objects becomes more mature, then this can be commercialized in terms of generating 3D printing out of these kinds of. You just draw something and you just ask the 3D printer to just print it, and it's been done. Right? You just draw an outline of a bag and ask the 3D printer, hey, look, I've drawn this bag. Can you generate me a real looking designer bag out of it? And it generates for you.
Very neat. Yeah, I like your aspirational visions of the future. Very cool. Well, to wrap up, as I mentioned, people can find the paper in the show notes. Where else can they go online to learn more about your guys' work?
We have written a blog of the paper. It's at arnabgho.github.io/madgan, all in caps. It's written in a much more easy to digest manner so that the core idea becomes very clear.
Yeah, I'll have that in the show notes too, and I recommend everyone check that out. Well, Arnab and Viveka, I want to thank you both so much for coming on the show and sharing your work. I think this is a really promising area in the image recognition and generation field, and I'm excited to see what you guys do next.
Thank you, guys.
It's a really good initiative of the Data Skeptic that disseminating knowledge in a very simplified format for everyone to digest, especially the AI revolution is coming up. So that's a pretty good job that you're doing. Thank you.
Oh, thank you very much. I'm glad you're enjoying it. Yeah, that's exactly our goals. We think that, exactly as you say, there's an AI revolution coming, and we want to help people understand it rather than fear it.
Absolutely.
Thanks for listening to Data Skeptic. Back in 2015, we did an interview with Anh Nguyen about his paper, Easily Fooling Deep Neural Networks. It's a very related topic to today's work, as well as the next interview that will air on Data Skeptic in 2 weeks. If you missed the episode with Anh, I went ahead and put that in the Data Skeptic bonus feed this morning. If you're not listening to the Data Skeptic bonus feed, head over to dataskeptic.com to check it out. While there, you can also get a Data Skeptic t-shirt in all sizes, or a hex sticker, if you want to show your support for the show. Los Angeles, Thursday, May 25th, coming up. I'm going to be speaking at Zephyr. If you want details on coming to that, look up the LA Machine Learning Meetup at meetup.com. I hope to see some of you there, and between now and then, I want to remind everyone to keep thinking skeptically of and with data.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.